In this section, we're going to look at the idea of graph theory. Now, graph theory isn't going to be similar to the functional sorts of graphs that you're used to with Euclidean graphs, right? When we talk about graph theory, we're basically talking about a set of vertices, right? And so basically, if we're looking at the diagram below, right, in this G, this is an example of what a graph would look like, all right, when we talk about graph theory. So we have a set of vertices, all right? The vertices are basically going to be these points where the edges meet, all right? And edge is basically going to be one of these sorts of lines or curves that connects two of the vertices, all right? So um, let's go through some basic terminology with respect to graph theory before we start answering any sorts of questions. So an edge is called incident upon a vertex if it basically is connected. All right, so in the diagram below, E8 is incident upon B. Two edges are parallel if they have the same endpoints. All right, so in the diagram below, we can see that E8 and E7 are parallel because they end up sharing C and B, all right, as the vertices. Now, we know from parallel, same slope in Euclidean sorts of geometry, but we're dealing with graph theory, all right? So don't necessarily think of it as necessarily like parallel having the same slope of two lines. Think of it more as like two wires that are connecting the same node together. All right. And most of you that are computer people, you could probably see the applications to networks. And for those of you that are engineers, maybe like road systems, things like that, where the vertices or stoplights or stop signs or something of that nature. Right. Adjacent vertices are two vertices that are connected by an edge. So down here, D and E are going to be adjacent to one another. A loop is going to be an edge that has one vertex. In the diagram G, there is no loop. A simple graph contains no loops or parallel edges. The degree of a vertex is the number of edges that are incident upon V. Right? So you just basically count the number of edges that come out of the vertex. The degree of a graph is going to be the sum of all the degrees of the vertices. The degree must be even, all right? If it's not, then there's no graph possible. And we call this the handshaking theorem or the handshaking lemma, right? If you wanted to prove that, you could prove that by contradiction fairly easily, all right? So let's go through and let's just go ahead and take a look at the graph below and determine some of the basic sort of fundamental definitions applied to graph theory. So we asked, is G simple? Why or why not? And we go back up to the definition of simple. Simple says that there are no loops or parallel edges. And we go up to parallel edges, same endpoints, right? So remember, I talked about already that E7 and E8 are both incident upon C and B. In other words, they both have the initial and terminal points on C and B. So we would say that no, it is not simple. So G is not simple. And the reason is that E7 and E8 are parallel, right? And that's good enough for us, right? We don't have any other sort of reason. We don't need any other reason except that we have parallel edges. Right? What is the vertex set of the graph G? All right, so this is letter B. And our vertex set is just going to be the set of all vertices. So we have A, B, C, D, and E. So we're going to write that in set form. And there is our set of vertices, our vertex set. We want to know what the edge set is. And the edge set is going to be the set of all edges. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would have E1, E2, E3, E4, E5, E6, E7, E8, and surprisingly, E9. All right. So those are pretty simplistic sorts of definitions so far. Name two parallel edges. Well, we already did, right? Remember we said that two parallel edges were E7 and E8, right? So we've actually answered that question already, but we could go through another pair. E5, E4 are parallel, all right? So we could say a pair of parallel edges are going to be E4, E5, okay? Another would be E7, E8. All right. So not that difficult, right? Just basic definitions of what our edge sets are with respect to parallel edges. Find the degree of vertex C and find the degree of vertex A. Okay, so we would say that the degree of vertex C, we can see that there's 1, 2, 3, 4, 5 edges that are incident upon it. So the degree would be 5. And then the degree of A, we look over here, we see 1, 2, 3, 4 edges that are incident upon it. All right, so not too difficult, right? It's pretty easy for us to do that. All right, so let me erase really quickly, give us some room so we can work the rest of this. And the next one says we just want to find the degree of the entire graph, all right? And that's not too difficult because we've already gone through and we found the degree of 2 of the edges. So we just need the degree of the other 3 edges, right? So we already have degree A, we already have degree C. So we just need for letter F here, we would say that we need the degree of B, and the degree of B is going to be 3. All right, and you can see 1, 2, 3. We need the degree of D, and that's going to be 2 edges, and then the degree of E is 1, 2, 3, 4. All right, so the degree of E is equal to 4. And so finally, the degree of the graph G is going to be equal to the degree of A, which is 4, plus the degree of B, which is 3, the degree of C, which is 5, the degree of D, which is 2, and the degree of E, which is 4. All right. And if we add all of those up, that should be 18. Right. So it'd be 7, 12, 14, 18 if I add those up. And that's good because remember we said by the handshaking lemma that the degree of G must be even, which it indeed is. All right, so that's a way to check to make sure that at least your answer makes some sense, is that you have to have an even degree for your degree of the graph. All right, so last thing we're going to do is we're just going to go through and name all the edges that are incident upon vertex D. All right, and that would be just E1 and E2. Right, so that's easy enough. So that's just our basic terminology with respect to our graph theory. Not meant to be anything too difficult as we start this out. All right, so now we know our terminology, and now we can move on a little bit. So another type of problem you might see is being able to construct possible graphs, okay? Or if it's not possible, explain why. So for letter A, we want to build a graph that has 3 vertices of degrees 1, 2, and 3. All right, and you might want to just pause the video and just try to do this for yourself, okay? Or if you have no idea how to do it, you can just go ahead and watch. All right, so for letter A, here's the way I would do it, is I would just call this one, like let's just call this A, and let's have this one, and let's probably call this B, right? And then finally, let's have C, and we can call this E1, E2, and then I can have a loop and call that E3. And if you guys look and see what the degrees of each of the vertices are, the degree of A is 1, all right, so that takes care of that. The degree of B is clearly 2, and then the degree of C is going to be 1, 2, 3. And when we have a loop, it contributes 2 to the degree of the vertex. All right, and so we've done it. We've created a graph that has 3 vertices of degree 1, 2, 3. Right. For letter B, we want a simple graph with 4 vertices, degrees 1, 2, 2, 3. And remember, simple graph, right? Simple graph has no loops, no parallel edges. All right, so let's see if it's even possible. And again, you might want to pause the video and try it for yourself. All right, here's the way that I would do this. All right, I would start out with this and have that. So that has degree 1, degree 2, and then we have this, right? And then we need a vertex of degree 3. All right, so we need one over here, And I think this will do it. All right, so we have 1. This now has a degree of 3. And this has a degree 2. This has a degree of 2 as well. All right, we don't have to name them. We just have to construct the graph. All right, and notice that this isn't a loop. Okay, a loop only has, it's connected by the same vertex. None of the edges are parallel, so that's good. And so I believe that this is going to constitute what was asked for us, a simple graph of 4 degrees, right? Now the last one is actually the easiest one if we notice what's going on initially. All right, so now this is where I'm going to encourage you not to pause the video and try to draw this, because if you try to draw this, you're not going to get too far, right? Take a look at the degrees of the vertices. All right, so 0, 2, 2, 2, 2, 3, 4. Well, 0 plus 2 plus 2 plus 2 plus 2 plus 3 plus 4 is going to end up being 19, I believe. All right, so we have 8 here. We have, oh, sorry, it's going to be 15. All right, so I think I added an extra 4 in there for some reason. All right, and so this is not possible, okay, because this is not an even integer. All right, and remember what we said earlier, that by the handshaking lemma, we have to have an even degree for our graph. All right, so that might be the first thing that you do before you even try to construct a graph. All right, so like up here with this animal right here, 1 plus 2 plus 3 is 6. All right, that's even. And then 1 plus 2 plus 2 plus 3, that's going to be 8. All right, and that's even. All right, but down here, 15 is not a z even. All right, and so it is just not possible to construct that graph. All right, so that's just some rudiments of being able to work with some of our graph theory stuff. In our next video, we're going to take this a step further, and we're going to start taking a look at the idea of some complete graphs, and then we're going to eventually look at some isomorphisms and some trees.